Let's start with units and measurements today. Coming to the first topic, that is fundamental quantities. So we have seven fundamental quantities with us: length, mass, time, temperature, electric current, luminous intensity, and amount of substance. So we have the respective SI units as well, right? Standard international units. These are length, it's meter; mass, kilogram; time, seconds; temperature, Kelvin; electric current, ampere; luminous intensity, candela; amount of substance, mole. We have mode of physical quantities. Those are plane angle and solid angle. So what does plane angle mean? Plane means x and y axis, means any two planes, right? If we consider a sheet of paper, it is considered as a plane. It is 2D, right? It has two dimensions. So such an angle formed in two dimensions is known as plane angle, and it has the unit of radian. Okay, we can measure the theta or d theta as arc length by radius, right? So this is the arc formed, this is the arc formed, and this is the radius. Okay, now coming to solid angle. So I consider a sphere. For example, a football or a basketball, right? Those all are spheres, right? So the angle formed within a sphere that is in three dimensions is known as a solid angle, right? So I measure it with the letter d omega. Okay, so here what is d omega? It is area divided by radius square. Okay, so here the unit is steradian, right? Now coming to the next thing, that is dimensional formula. What are dimensional formulas? So dimensional formula is a type of letter or a formula used to represent a particular physical quantity. For example, if I have length, okay, I will represent it by capital L. So these all fundamental quantities are the base of all other quantities, right? If I talk about speed, what is speed? It is distance traveled in unit time, right? Distance is what? Length again. In unit time, time is what? Again, these two are physical quantities. If I take any of the derived quantities or any quantity, they are always made up of these fundamental quantities. So to represent them in the form of fundamental quantities, we need dimensional formulae. Okay, so for length, it is capital L. Okay, so we use square brackets for specifying dimensional formula. Okay, for mass, it's capital M, right? For time, it is T. For temperature, it is Kelvin. So here you may get confused. For temperature, it is Kelvin, while for time, it is T. Okay. For electric current, it's ampere. Right. So for mole, it's mole only. This small letters you can see. Right. So these are all the dimensional formulas. So, but the plane angle and solid angle, these two do not have dimensional formulas. Why they don't have? Let's look into their formulas. Right. So what is d theta? It is arc length by radius. Right. Again, arc length means it is a fundamental quantity L, having the dimensional formula L, right? Radius is again measure of something in terms of length, right? Again L. So this L will just get cut off. So the remaining is no 0, 1, right? So it doesn't have any dimensional formula, plane angle as well as solid angle. Solid angle also, if I say area, what is area? Length into breadth. That is the square of two dimensions, right? So if I talk about length into breadth also, it is L into L, that is L square. Down also I have radius square, that is divided by L square. So the whole thing will get cut off, and the solid angle is also a dimensionless quantity. Okay. Now coming to the next topic. Okay. So in the given equation, so now what we can do with these dimensional formulas, what are the uses of it, right? So first use is finding the dimensional formula of an unknown quantity, right? Or a known quantity as well. Or we can check the dimensional correctness of an equation, right? So the first main rule is quantities having same dimensional formula can be added or subtracted. Okay. For example, we have a question here. Okay. So in the given equation, v is equal to x plus at, wherein v is velocity, a is acceleration, and t is time. Find the dimensions of x. So we know that quantities with same dimensional formula can be added, right? So the dimensional formula of velocity should be equal to the dimensional formula of acceleration into time, which should be equal to the dimensional formula of x. So what is the question? Find the dimensions of x, right? Simply we can equate it. Now how did I get this Lt raised to minus 1? So I have v velocity, right? What is velocity? Speed. It is distance L divided by time, right? So here both are having power 1, right? So when I will bring this t in the numerator, that is the top, it will become t to the power minus 1, right? And again here, mass is not there, so m to the power 0. Okay, so we usually represent lot of quantities are represented in the form of m, l and t. So here we have written the general form, that is m raised to 0, l raised to 1 and t raised to minus 1, right? Now deducing relation among physical quantities. Okay, so with this dimensional formula, we can also deduce or conclude relations between different physical quantities. How? Let's see. So the question is, derive equation for kinetic energy of a body moving with mass m and velocity v. So we already know that kinetic energy is half mv square. But here we need to prove that we have a formula between mv and kinetic energy, right? So how will we prove it? So we'll first take out a simple statement that kinetic energy is directly proportional to m raised to x and v raised to y. If it is inversely proportional as well, then the powers would be in the minus form, right? So taking the simple general form, that is m raised to x, v raised to y. So to remove this proportionality symbol, I'll add a constant k, right? Any constant. Okay, now I should know the dimensional formula of kinetic energy. So what is the dimension of kinetic energy? It is m L square t raised to minus 2, right? It is ml square t raised to minus 2, right? So we know that kinetic energy is in the form of work, right? Work done is kinetic energy, right? This much is work is done means this much kinetic energy is used, right? So we can also say that work done also has the same dimensional formula. So a simple way to find the dimensional formula is F, that is force, dimensional formula of force into dimensional formula of displacement. What is the dimensional formula of displacement? It is L, right? So for force, what is it? Ma. What is the formula for force? Ma, that is mass into acceleration, right? Now what is acceleration again? It is v by t, right? Velocity by time. What is velocity again? You need to relate like this. L t raised to the power minus 1 is velocity, divided by t again, that is lt to the power minus 2. M is same, mass is same, right? M only. And from here, acceleration is lt to the power minus 2. And this whole thing I am multiplying with this L of displacement. So what I'll get? Ml square t to the power minus 2, right? Which is this one, ml square t to the power minus 2. So the dimensional formula of every form of energy, whether it be potential energy, kinetic energy, as well as work, is ml square t to the power minus 2. Now coming back to our relation. Okay, so we took that relation that k is some constant into mx, m to the power x, v to the power y. So again, v is what? Velocity. Let's take it down into l to the power l t to the power minus 1, right? And what? Mass is m only, right? So this k into m raised to x we have, and in bracket lt to the power minus 1. So what will happen here? I'll get, when one more step we'll write k, mx would remain as same only, right? See, here you can see, comparing the mass terms, mass and mass. So what is x here? Here m raised to 1 is there, and here we have m raised to x. So which implies that x is equal to 1, right? So now we have mass, right? We got to know what is the relation with the mass. Now let's see the relation with velocity. So here we have y. So multiplying this y with both of these, that is L raised to y, t raised to the power minus y, right? So now comparing with this equation again, what is L to the power y? It is L to the power 2, right? And what is t to the power minus y? It is t to the power minus 2. So this implies that y is equal to 2. So what we can say, it is kinetic energy is equal to a constant into mass into velocity square. So this is our actual formula, right? Half mv square. Just the constant here, K, is half, right? Yes. Now coming to what are the limitations of dimensional analysis? It checks only the dimensional correctness of the equation and not the exact correctness. What does this mean? It means that if I have a simple equation, right? So if I have a simple equation like V is equal to U plus AT, right? So here we need U, right? What is U here? U is initial velocity. V is final velocity. A is acceleration. T is time, right? So here we check this that it's dimensional correctness, right? So we will have the same dimensional formula as U. U will have the same dimensional formula as AT. But this is the dimensional correctness only. Instead of this, if I write instead of this correct equation, if I write U is equal to V plus AT, right, which is wrong, right? So such a formula does not exist. This is wrong formula. But the dimensional formula will not tell us that the formula is wrong or exchanged, or the places of the sum, dimensions have exchanged. It will only tell us that dimension of U is equal to dimension of V, which is equal to the dimension of AT. It will not tell us the actual correctness of the equation. Okay. Now, dimensional constants cannot be obtained by this method. Yeah, truly. So here the constant value is half, but we did not get the half value, right? So next is it does not distinguish physical quantities with same dimensions. As we discussed here in the same example, kinetic energy is not being differentiated with work. They both have same dimensional formula, right? So the next term, formula containing trigonometric or exponential or logarithmic functions cannot be derived from this method or dimensional analysis method. Okay. So these were the limitations of dimensional analysis. Now coming to what is accuracy and precision. Okay. So accuracy is a measure of how close the measured value is to the true value, while precision tells us to what resolution or what limit the quantity can be measured. For example, taking a simple scale. So what is the precision of the simple scale? It is 15 centimeters, right? It can measure only 15 centimeters, right? But what is accuracy? While I am measuring, right? While I am measuring a simple small eraser, let me assume, right? So if that eraser is 2 centimeters, or let's take 5 centimeters, and inside that it is 0.1 mm, right? So the normal scale will not show me 0.1 mm. So it is not an accurate measurement, right? So it is the closest value it has shown me that it is 5 centimeter, right? So 5 centimeter is the closest value, but the actual value is what? 5.01, right? So the true value is 5.01, while the accuracy is 5 centimeters, right? And what is the precision of that scale? What is the limit? It is 15 centimeters, right? Or what is up to what resolution if it is asked? Then what to resolution is centimeters, and maximum it is in 0.5, that is 5 meters, and 5 centimeters done. Then in the form of millimeters, right? Simplest millimeters, that is 5 millimeter, till that it can show, right? Now coming to errors. What are errors? So we have two types of errors: systematic errors and random errors. Systematic errors are caused, they have three types. Okay, either it is an instrumental error, or imperfection error, or personal error, right? So what can be these? First is instrumental error. The instrument itself is having some error. So what can be those errors? Those errors can either the markings on the scale have missed out, right? Or they have erased because of the oldness of the scale. Many days have been taken, right? It has been taken. So the oldness of the markings on the scale have been erased, right? So this is instrumental error. Imperfection error is that you keep the scale slanting and you are measuring it. It's wrong, right? Personal error can be like, yeah, the same thing. That is, you kept it slanting and you are seeing from a different angle, right? So, or you have kept it perfectly, but you are seeing from a wrong angle, right? So, these are all the different types of systematic errors. Now, what are random errors? Random errors, the best example is least count error. Now, what is that? What is least count? Least count is the smallest value measurable with an instrument. right? With a normal scale, the smallest value is 0 centimeters, right? The least count of our normal daily use scale is 0 centimeters, right? So the error with this least count are known as least count errors. Now coming to associated errors with the least count, right? What are the errors associated with the least count errors? First is absolute error, relative error, and percentage error. Coming to absolute error. What is absolute error? How to calculate it? It is the true value minus the measured value. So taking the same example, that I measured a eraser which is having true value of 5.01 centimeters. But the measured value according to my instrument is 5 centimeter only. So what is the absolute error? It is 0.1 centimeter, 0.01 centimeter, right? So what is the relative error? It is the 0.01 centimeter, that is the absolute error divided by our true value. What is our true value? It is, just a second, it's looking like 9. Yeah. So absolute error, that is 0.01 divided by our true value. What is our true value? It is 5.01. Right? So now percentage errors. So this whole thing into 100. It is just the percentage of relative error. Right? So now coming to, we have a question here. Check the dimensional correctness of half mv square is equal to mgh. So we know both are energies, right? Half mv square is kinetic energy, mgh is potential energy, right? So half mv square, okay, we have to, first step is we have to ignore the constants, right? So half is ignored, then we have mv square, right? So mv square, we just saw m l square t to the power minus 2. So in mgh, again, what is g? G is a form of acceleration, right? G is a form of acceleration. So acceleration, we saw it is lt to the power minus 2. Again, h, what is height? It is L again, measure of height, length, right? So again, we will get ml square t to the power minus 2. So LHS is equal to RHS. Equation is dimensionally correct, right? Yeah. So now coming to combination of errors. So addition or subtraction with errors. Okay. Now if we have some errors, so how to add or subtract them? For example, we have here A plus or minus delta A. Delta A is the error, right? Plus or minus B plus or minus delta B, right? So this is the error with the first object that we have measured. This is the second object, right? So if you want to add these errors, or it may be the values measured first time and values measured second time of the same object, right? So what we need to do, we need to add the true values, right? Plus or minus, we need to add the measured values. These are measured values, right? Plus or minus the same, okay? Plus or minus delta A plus delta B, that is the absolute errors, okay? We have to add both the absolute errors differently and we have to add both the measured values differently, right? So we will finally get Z plus or minus delta Z, right? How to multiply or divide? So if Z is equal to AB, right? If Z is equal to AB, then Z plus delta Z would be what? Multiplication, right? That is A plus or minus delta A. That is the measured and the error during the first measurement, and measurement and error during the second measurement. We have to multiply them. So when we multiply, what will we get? So multiplying this A with this B, AB. Okay, this A with this B plus or minus B, right? So A delta plus or minus B. Again, this delta A with B, right? So plus or minus B delta A, and this delta A with delta B, that is plus or minus delta A delta B. So dividing LHS by Z, okay, and RHS by AB, right? So this term, which is the LHS, we are dividing it by Z, okay, and this RHS, we are dividing it by AB. So what will we get? So here when I divide the whole term by Z, what I'll get? I'll get 1 plus or minus delta z by z is equal to 1 plus or minus. Why? Because I have dividing it by AB, right? So this term becomes 1 plus or minus dividing it by AB, right? So AA gets cancelled, plus or minus B I got, right? Plus or minus delta B by B. Again here I am dividing by AB. BB cancel, delta A by A plus or minus delta A by A. Again here I am dividing by AB. So I am getting like this, that is delta A by A into delta B by B. Okay, so this is when we multiply or divide errors, right? So now coming to conversion of CGS units. So we have CGS as well as MKS and SI unit systems, right? So coming to CGS system. So firstly, we have SI unit system that is followed by the whole world, and CGS system as well. So what is CGS? It is centimeter, grams and seconds. Okay, CGS systems. So here in CGS system, 1 Newton is equal to N2 times. Okay, so let's convert it. Okay, let's find out 1 Newton is equal to how many times. Okay, so we know that 1 Newton is 1 kg meter per second square, right? And this N2 value, which is in CGS system, we want it in grams and centimeters, and seconds is common thing, right? So I want it in grams. So what I'll do? First step, I want it in grams, right? Kg to grams. I'll multiply it by 1000, right? So, and here it is in meter, I want it in centimeter. So I'll multiply it by 100, right? And again, I have here gram per centimeter, gram per centimeter. So these all will get cancelled out. I'll have 10 to the power 5 as my N2. So 1 Newton is equal to 10 to the power 5 dynes. Okay. Similarly, coming to joules for energy, right? Newton is for force, joule is for energy, right? So 1 joule is equal to 1 Newton into 1 meter, which is equal to 10 to the power 5 dynes that we just calculated into 10 square centimeter. So 1 erg, ERG, is equal to 1 dyne into 1 centimeter. Okay. So as we have 1 joule is equal to 1 Newton into 1 meter, 1 erg in CGS unit is 1 dyne into 1 centimeter. So what is 1 joule? It is 10 to the power 7 ergs. Okay. Now coming to rules for rules for significant figures. So all non-zero digits are significant. So you need to remember this. Okay, all non-zero digits are significant. For example, 2, 3, 4, 3 significant figures, right? All zeros that appear between 2 non-zero digits are significant. What does this mean? This means that if I write 2, 0, 2, then here I have 3 significant figures. The between 0 is also counted, right? Because 2 are non-zero digits, right? 2 is non-zero digit. And between 2 non-zero digits, I have a 0. So it is counted a significant number there, okay? All zeros between decimal point and the first non-zero digit are insignificant if the value is lesser than 1. Now, here we have 0.002045. Here the value is of course lesser than 1. First condition true. Second condition is what? It should be between decimal point. Okay, it is between decimal point and the first non-zero digit. What is the first non-zero digit? It is 2. Right? So, of course, these all zeros are insignificant, not important. So, what are the 4 significant or important figures here? Number figures. These are 2, 0, 4, 5. Why again this 0 is counted between 2 and 4? Because it is between 2 non-zero numbers, right? Coming to next one. All zeros to the right of the decimal are significant. To the right of the decimal are significant, though there are no non-zero digits following the 0. Means what? If I write 16.00, here, though there are no numbers following those 0 zeros, but still these 2 zeros are to the right of the decimal, and so they are important. And this 16.00 has 4 significant figures. Okay. Now, all zeros to the right of the last number. Okay, and here the condition is the number should be greater than 1, right? Here we should have the number greater than 1. So all zeros to the right of the last non-zero digit are insignificant. Means what? All zeros to the right of the last non-zero digit. Now what is our last non-zero digit here? 5. To the right means this side. What are there? There are 2 zeros. So these two are not important, insignificant, right? So we have only 3 significant figures, 6, 0 and 5. And we know why this 0 is significant, because it is between two non-zero digits, right? Now, coming to all zeros to the right of the last non-zero digit are significant only if they come from a measurement. If I write centimeter or something, only then they are significant, right? Now, coming to rounding off rules. Now, how to round off some numbers, right? So, if the last digit is lesser than 5, then it can be ignored, right? What does this mean? That is 4.762 if I take. So, 6, 2, right? So, this 2 is of course lesser than 5. So, I'll ignore it. If I want only 2 places, I'll ignore that last 2. I'll get 4.76, right? If the last digit is more than 5, preceding digit should be raised by 1, right? And the last digit should be omitted. That is, see here, if I have 4.729, of course, 9 is greater than 5, right? So what I'll do, I'll increase this 2 by 1. That is, it will become 3 and omit this 9. So what I'll get 4.73 as my rounded off number, right? Now coming to, what if the last digit is equal to 5, right? We saw if it is greater than 5, we saw if it is lesser than 5. What if it is equal to 5, right? So if the preceding digit is even, then 5 can be ignored. That is 2.34 I have, 345, right? So before 5, what is there? 4, which is even number. Then I will ignore that 5. But if the preceding digit is odd, then it has to be raised by 1. What does this mean? If I have example 2.315, so 1 is odd, right? Before 5, 1 is odd. So 1 will become 2, raised by 1, right? In addition or subtraction, the number of minimum digits after decimal point is noted. Means what? In addition, if I am adding or subtracting two numbers, okay? So here I'll get a big number, right? And now you can see here, what is the smallest number of decimal places? That is 2 decimal places, right? Here 2 decimal places, here 3 decimal places. So what is the smallest or the minimum digits after decimal point is 2. So in the final answer also, I will keep the minimum digits of decimal places, that is 2. Okay. Now coming to the last point, that is multiplication or division of number of significant figures of the resultant is equal to the minimum number of significant figures present in any component of the multiplication or division. For example, if I want to do 6.52, which is having 3 significant figures, right? 6, 5 and 2 into 1.2, that is having 2 significant figures, 1 and 2, right? So I'll get a number 7.824, which is having here 3 plus 1, 4 significant figures, right? So what I have to do? So this is having 4 significant figures, right? So what is the least number of significant figures I have? It is 2 here in 1.2. So in the final answer also, I should have only 2 significant figures, that is 7.8, right? So with this rule, we finally end the chapter, that is units and measurements, the first chapter of physics. So I'll just scroll the notes once. Yeah, so we did with fundamental quantities done, right? We also discussed about dimensional formulas. What are the uses of dimensional formulas? How to solve questions based on dimensional formulas, limitations of dimensional analysis, and accuracy and precision. Then types of least count errors, right? Then combination of errors, that is addition and or subtraction, and multiplication or division of errors, right? And conversion into CGS units, rules for significant figures, right? In that we saw 6 rules, right? And we also saw rules for rounding off the numbers, right? In that we saw 5 rules. Okay, so here were the notes. Okay, thank you for watching.